manufacture metallic materials, surface engineering, mechanical metallurgy, experimental tribology, fatigue and fracture of engineering materials, structure property correlation. We are very glad to have you, sir, and I request Dr. Anand to take over the session. Thank you, sir.
Okay, great. Mahesh, I think it is audible, right?
Yeah, yes, sir, you are audible.
Okay. Thank you. Thanks for that kind introduction. So, probably without much ado, let's get started. Let me start sharing my screen. Hope the slide is visible, Mahesh.
Yes, sir, it is visible. Can you
Okay.
just put in a slideshow
Yeah,
mode?
yeah. I'll go it.
Yeah.
I'll get into it. So, yeah. All
Yeah.
right. I think it is perfect now.
Yes, sir, exactly.
Okay. All right. So, firstly, very good morning to all of you, and Mahesh, thanks for this opportunity. Uh, so I hope the participants have gone through I think, 3 days of the other interesting talks. And today I've planned my talk titled The Role of Additive Manufacturing in Remanufacturing Applications. Okay, so we will dwell upon probably in the first of my talk the role, introduction, and the different types of additive manufacturing technologies. And in the second part of my talk, I would be more emphasizing on the remanufacturing or the refurbishment, or it can also be called as repair kind of applications. All right. So moving forward, this is how I've organized my today's talk. The first part would be more emphasis on introduction to AM technologies and the different types of AM processes. And the second part would revolve around the role of AM, especially for remanufacturing aspects, especially in the aero industries, right? So we will try to look at why more specifically on aero industries. And finally, I would be, concluding my this particular talk. All right. So let us get into the first part of my talk to get understanding and introducing probably I assume that the participants might be uh, having a fair idea about additive manufacturing process, but in the interest of giving the completeness of this presentation, I have organized and also had some of the emphasis why we need to get into this AM process, right? So now, in that context, if we look at when we try to compare the conventional manufacturing process versus the additive manufacturing process, then it becomes easy for us to probably appreciate the potential of this additive manufacturing process. So in that context, if you look at quickly how a component or a part would be manufactured through a conventional manufacturing route, is that we take a, let's say, a solid workpiece, and then we try to hold it in a, let's say, in this case we are dealing with, let us assume, a CNC machine. Then appropriately we need to hold them by using appropriate fixtures and the jigs, so as to accomplish the process of this machining, and then subsequently in order to get a this sort of a material removal, like in the form of step, and also we might be introducing some of the blind holes or through holes that can eventually have a leading to a end use part, or it might be getting into a sub assemblies in the whole of a complete end use application, right? So if you look at very carefully in this conventional machining process, starting from the solid workpiece and leading to a final finish part. What we have to go through is that the final objective of getting the required dimension, right, and also the accuracy of this final part would greatly depend on how we get started with this particular solid material, and then how do we assemble them or hold them in the fixture, and how do we maintain the cutting tool and the workpiece relation, right, during machining. There could be some deviation in terms of introduced by the cutting forces, due to which if improper clamping or fixing of this component is there, then it can lead to deviations in the expected final dimension of the end use component, right? So what I'm trying to emphasize is that the final accuracy, especially the geometrical and dimensional accuracy, is what I'm emphasizing, number one. And also the time taken for to accomplish this final part would be again would be quite longer. And other important thing is that we are also wasting a lot of material in the form of chip removal, right? And then they get into the scrap. So the kind of that's why we also call this form of manufacturing process as a subtractive manufacturing process, because of the fact that we are removing material, right? So we do see that although it's a conventionally followed manufacturing route through several decades, we have challenges in terms of finally obtaining the in terms of accuracy, number one. Number two, we are wasting a lot amount of material in the form of chip. And the third thing is the time taken from when we start from a workpiece to the final end use application part. The time taken is quite long, because of the fact that you need to move from, let's say, one position to the other position. Maybe in the case of CNC it might be happening in the single machine itself, but in the conventional route, if you recollect, if we want to make it with the milling machine and then moving into a drilling machine, so the alignment issues, associated fixtures, time taken, all those things play a greater amount of time. And during that course of period, you will see that eventually the cycle time to obtain the end use part is relatively higher, right? So can we overcome these issues with the additive manufacturing process, is what we are trying to advocate and try to see the similar kind of component through additive manufacturing process. So I hope the audience is aware of the additive manufacturing process, where we try to fabricate the final end use application with, the part in the fashion of layer by layer approach, right? And then subsequently we can create these steps and also the holes in a one shot, right, without in fact removing or wasting of the material. And also the alignment issue or the accuracy issue can be in fact minimized. And also the time taken by this process compared to the conventional manufacturing route can be drastically reduced, right? So this is I've tried to emphasize in the by taking an example of machining process. The same thing can be looked at by looking at the process like conventional casting process or metal forming process, where uh, there is always issue with the workpiece and the tool in the case of machining, or workpiece and the die material in the case of metal forming process, right? So these things can be overcome, and then eventually we can try to obtain the final product by within a less cycle time, and with much better dimensional as well as geometrical accuracies, and also the minimal wastage of the material, right? When we talk of dealing with expensive materials, which is the case for most of the aerospace application, materials like titanium, super alloys, they're all very expensive. And if we can save those materials, like from the switching over from subtractive manufacturing approach to a additive manufacturing approach, we can in fact save a lot of material, right? So uh, so the takeaway from the slide is that we do get a lot of incentives when we switch over from conventional manufacturing approach to a additive manufacturing approach. That is the takeaway from this slide. So now, if we try to compare what is the rewards one can get, right, when we switch over from conventional manufacturing setup to additive manufacturing setup, obviously the industries are focused on the profit. So they will try to look at what is the cost I'm incurring per part when I have additive manufacturing route compared with conventional manufacturing route. So this particular graph would try to give us a fair idea for us to take a call when we need to make use of this additive manufacturing setup, and then the conventional manufacturing setup for a given part, right? And that is of course decided by what is our number of product that we need to manufacture, right? So if you carefully observe, this blue color line is your conventional manufacturing setup. You can see that um, when we have very less part to be manufactured, obviously our conventional manufacturing route will have higher cost. And as we increase the number of part to be manufactured, let's say when we move over from job type production to mass production, then obviously the conventional manufacturing route is going to be rewarding. And if you look at the red color line, of course, it is for additive manufacturing technology called selective laser melting. We will quickly look at what is that technology in the upcoming slides. But here, if you look at, it is in fact independent of our number of parts. The cost is going to be very constant, no matter how much number of component we need to manufacture. So when we compare the additive manufacturing and the conventional manufacturing, we do get a break even point, and from here we can try to appreciate the additive manufacturing route to be a very economically viable when we have very low number of parts to be manufactured, right? And on the other hand, when we have a high volume of parts to be manufactured, then obviously we see that the conventional manufacturing route or approach would be rewarding in terms of obtaining less number of the cost to be less compared to the SLM or AM technology. And in fact, this AM technology is also trying to move towards decreasing the cost in terms of working on different aspects to increase this productivity issues by changing the architecture or the instrumentation in the AM technology. Thereby, in fact, it can catch up with the conventional manufacturing cost, right? So that is in fact in the research phase, people are trying to do this, increasing the productivity in terms of AM or SLM process by increasing the build speed or printing speed, and also by having, which can be accomplished by using more number of laser beams. We'll see how does it help, right? So thereby we can in fact try to decrease the cost associated with the AM technology, right? So the takeaway is that from this graph, whenever we have very low number of parts to be manufactured, obviously our additive manufacturing setup or the approach would be costing less compared to conventional manufacturing route. On the other hand, if the production volume is very high, then there is no other choice, switching over to conventional manufacturing process from the additive manufacturing process, due to the fact that we can decrease the cost associated with the part that we are going to manufacture, right? And now looking at again the cost comparison from the viewpoint of what is the complexity of the part that we need to manufacture. Like for example, if you look at, this is example of let's say the engine block which could be used in a automotive sector, where you try to see that the shape and also the kind of dimensional accuracy that we need to obtain, all those things would be quite complex compared to the simple geometry that we need to manufacture through conventional manufacturing route. Then our slmr additive manufacturing process again tries to play a role in terms of decreasing the cost, as we as there is we as we see more complicated profiles or geometries that we need to manufacture, right? So uh, on the other hand, the conventional manufacturing route, as the complexity of the part increases, we tend to see that the cost keep increasing, right? On the other hand, as we saw in the previous slide, the slmr, the additive manufacturing technology, the cost is going to remain same no matter whether the complexity is simple or more complex. It is going to be a more like a cakewalk for this technology, and thereby the cost associated with producing such part can be minimized, right? So that is in fact could be very rewarding when we look at, particularly in the case of aerospace components, which would have a more like, not only in terms of performing the load bearing applications, right? um, we can in fact, by using additive manufacturing technique, we can try to induce the component to behave or to satisfy some of the functional requirement also. For example, if we look at the turbine blade, right? If we can have some sort of internal structures or the cooling holes, right? Then we know that this turbine blade, when it is operating at the high temperature, would be subjected to the creep kind of associated damages, and those damages can be mitigated when we can have the internal structures in the form of cooling holes. Then apparently we can increase the life of such turbine blades, right? And in fact, we can also make use of this particular additive manufacturing technique to fabricate very expensive molds that could be used in the conventional casting process. We can create such molds, and we can in fact have appropriate internal cooling mechanisms to increase the life of such molds, thereby the cost can be justified. And as we have seen, the am technology is independent of the part complexity. No matter how complex is your part, we can print it at ease compared to conventional manufacturing process. And again, the am technique is also very helpful in fact having the concept of part consolidation, which means that when you have more number of parts to be assembled, and then which would be satisfying your end requirement as a single component, right? In the conventional route, people used to manufacture small different sub assemblies, and then try to integrate them, assemble them together, thereby we will finally get the end use part. But in the case of additive manufacturing route, no such assembly operations are required, because we are actually
consolidating all the such small assemblies. I have an example in the upcoming slide. So thereby we can actually decrease number of assemblies and also the risk associated with them. Thereby we can produce as a single part itself, right? So in view of all these things, we can see that the additive manufacturing process is really rewarding compared to the conventional manufacturing processes, right? So now moving ahead, I have just charted down four key aspects why additive manufacturing process is really helpful, right? Like for example, the first one is through this additive manufacturing route, we are getting what is known as the design freedom, right? So for the designer, there is always concept of you can't actually design a component just like that. It should also have some not some, it is also should be manufactured, right? So the manufacturability aspects also need to be taken into consideration. Then the design has to be compromised, and then accordingly you have to look at whether it is manufacturable or not. So such kind of compromise from the design point of view, the designer used to work upon, and the part used to go through a lot of design iterations. So when we need to manufacture that part, especially through the conventional route like machining, casting, or the metal forming sort of a process, right? So but in the case of additive manufacturing process, in fact we are getting such design freedom. That's why in the previous slide we looked at the additive manufacturing process is independent of the complexity of the process, right? But on the other hand, the conventional process, the as the complexity increases, the manufacturing cost goes high, right? So we can obtain design freedom. That is one of the rewarding feature when we switch over to additive manufacturing process. And when we have a low quantity kind of parts to be manufactured, we also looked at in the previous graph, the additive manufacturing route is very economical when we have low quantity to be manufactured, right? So obviously we can't go for conventional manufacturing process for a very less number of parts to be which we need to manufacture. Then if we have to go, obviously we have to pay more cost for such a manufactured part, right? So in fact we can get this particular low quantity economy can be obtained achieved through this additive manufacturing route, right? And we have another in fact key benefit when we look at this additive manufacturing process as a technique for manufacturing part, is that we can actually predict what is our production rate could be, right? And that is going to entirely depend on what is your part design. And once we have the part design in our hand, in fact we can actually calculate how much time I'm going to spend to produce one part, and subsequently for achieving target of the customer's requirement. Let's say for 100 components to be manufactured within 1 month, then subsequently we can take a call whether it is possible through aim, I mean through aim route for that given complicated profile and the shape and size, right? So we can in fact predict the production rate. And in fact the other key feature which one can obtain when we switch over to additive manufacturing process is that we can reduce the assemblies, right? As I said, the part consolidation, when we have whenever the case for obtaining a final end use part or the component, if you have 100 sub-assembled part would lead to a single piece of the end application part, then subsequently we can reduce as much as possible and try to consolidate them and then try to integrate two parts wherever possible into one part, right? Then thereby we are in fact reducing the assembly time taken to realize the end parts, which would be rewarding in terms of increasing the productivity, number one. And also we also know that whenever there is assembled part, especially for dynamic situation, or the component subjected to dynamic loading, when there is a assembly, then there is a more chances of risk, and then such kind of risk would lead to less life of the component. So those aspects can be mitigated when we reduce the assemblies. All right. So now with that background, let us move forward and try to understand what are the kind of maybe quick benefits one can think of. This would be in terms of the parts, right? When we want to reduce the cost to produce a part, the cost of the part in terms of manufacturing can be cut down at least 50% when we move from the conventional to additive manufacturing. By doing so, in fact, we can reduce the scraps, especially from the subtractive manufacturing route. And the other aspect is that the buy to fly ratio, it is more to do with what is the raw material you started with. Let's say we started with 100 kg of raw material, and eventually your end use part is weighing 2 kg. Then the buy to fly ratio would be very high in the case of conventional manufacturing setup. On the other hand, in the case of additive manufacturing, the raw material that we are using more or less completely used for to obtain the final part. So that's why we say buy to fly ratio in the case of additive manufacturing is 1:1. Thereby we can save the scrap rate, right? And the time to market is by in terms of productivity has been cut down by at least 64% when we switch over to additive manufacturing route. And in fact, there is also another rewarding point one can get by using additive manufacturing setup, is that the part weight, right, can be cut down at least 64%, right? We'll look at it, how do we do that actually, right? So this is another advantage. So this is the overview of the benefits one can get when we switch over from the conventional manufacturing setup to the additive manufacturing setup, right? So now some of the value addition which we can add or obtain from this additive manufacturing route is are the following. Like, as I mentioned, the designer will get a freedom in terms of getting a part consolidation, which is nothing but reducing the number of parts which will be getting into the assemblies. This could be one example. And then you have what is known as the lattice structure or the topology optimization, which we can get by which would be very rewarding in terms of reducing the weight. I'll show you through a example how do we do that. Like, for example, this is the lattice structure and the topology optimization strategy through which we can obtain this part. Assume that through conventional route you can't these are all, it is almost like a skeleton type of a structure. That is what we call it as a lattice structure. And to obtain these kind of structure through conventional route is not possible, or it would be really really challenging. But the through a aim route we can obtain that. uh, it is it the much more point to be focused here is that uh, since I said through conventional manufacturing setup, since it is challenging, people try to make use of this whole assembly as a solid assembly, right? The moment when we have solid sort of a part, then obviously the weight of this whole component would be higher compared to these kind of skeleton structure or the so-called lattice structure. So this would contribute in terms of reducing the weight. right, for this component. And such kind of weight reduction or light weighting would be cost rewarding, especially for aerospace application, because the kind of fuel consumption that we can save by saving the weight which would be incurred or through these parts would be cost rewarding, right? And also the intricate and complex internal structures is also one of the value addition or the kind of feature one can get from this route. This is the kind of internal structures and then complicated surfaces one can think of from this AM to be manufactured. And there are other various advantage one can think of is that multi-material design possibilities, we can combine two or three materials to produce the part so as to cater to the end application. And also the design for mass customization can also be done. And the part repair and remanufacturing is another area where people are looking at this additive manufacturing as a game changer. That is what I'm going to cover in the second part of my talk, right? So now, having understood the AM and importance, how it is better or superior compared to conventional manufacturing setup, the different types of AM technologies have been evolved over the period. And as per ASTM F2792, people have classified at least 7 types of AM technologies, right? They are broadly classified as a liquid based process, solid based process, and powder based process. So what does it mean, liquid, solid, powder? These are all nothing but what is the starting material that would be used in this AM technology so as to finally obtain our end use component, right? So accordingly these classifications have been evolved. Okay, and we can, I'll show you some of the videos depending on different types. And again, this AIM technology can also be broadly classified under direct AIM technologies and indirect. And whatever we saw in the previous slide, according to ASTM designations, the liquid based, solid based, and powder based, we have in fact variant types of AM technology which has been evolved. And the other interesting domain where this indirect AM technology, which is gaining more importance, is the casting with AM patterns, which we can do, and the direct AM molds. We will look at them, how the part can be manufactured through this indirect AM technologies as we move forward, right? So now, uh, having understood different types of AM process, how they classify, the typical process flow in AM technology would be the following. Like, for example, we would be starting with what is the starting material. As we looked at, the material can be liquid, solid, powder. Then eventually, if we are, let's say, taking of powder, then we have to really focus more on what is the kind of powder purity, because as this powder becomes the starting material for our part, the purity of this powder would dictate the kind of performance that the manufactured part would be, delivering to us. And the powder size, because we can't manufacture or print any size of the powder through this route. There is a typically flowability aspects would be attained with certain grade size of the powder size, and what kind of material we use, so on and so forth. And same is the case in terms of we have to more worry about how do we design in terms of printing our part. Like, for example, that would mainly depend on what is the type of geometry of the component that we are trying to manufacture, and whether they have some sort of overhangs. Then apparently, if they have overhangs, we need to give some sort of a support structure for such overhangs. And eventually these aspects will be covered or thought about, very involved kind of a process in the design phase, and the kind of layout when we manufacture this part, in what kind of configuration we are going to manufacture them, whether we are going to keep this part on a horizontal kind of a direction, vertical direction, or inclined orientation, and what kind of uh, job proximity, like a component, whether we can print only one part at a time or multiple part at a time, and what kind of chamber, I mean, the atmosphere maintained inside the chamber within which the part would be manufactured, right? And also the process, from the process point of view, this is more specific in terms of the laser based am route, where what kind of laser intensity, speed, and exposure pattern, so on and so forth. In fact, close to 180 kind of parameters are need to be worried about when we think of laser based additive manufacturing process. Once we manufacture, in fact, we need to also worry about the post processing aspects of this am technique. Typically people would go for this heat treatment kind of techniques for metal am kind of part when we are manufacturing them, because of the fact that during this am technique or processing, there would be residual stress, predominantly tensile residual stress will get developed, and we need to make use of this heat treatment or stress relieving operation. And also the short peening and polishing sort of aspects would also be used, because of the fact that in the as printed or as manufactured condition, the surface roughness would be slightly high. And all those things in fact would dictate what is the kind of component accuracy, both in terms of dimension and geometry, and the surface quality, more importantly what kind of surface roughness and surface finish, and the property of this component which we obtain at in the component level, right? So all those things would be studied or investigated meticulously before getting into the component level. uh, People would be doing it at the sample level and then try to understand for the new materials, right? So but for most of the am material, this approach or the process flow is being already established. And I encourage the participant to look at the journal papers for the most of the am material which has been already established, right? And there are additional aspects would also be looked at when we actually look at from the engineering design loop point of view, when we try to look at the weight optimization, especially when we are looking at the weight reduction or light weighting kind of application for aerospace sort of end use application. This flowchart or the kind of loop would be go through a kind of iterative process in order to optimize and then finally validating them and then certifying them. So in fact, this particular dfam is one of the a very important phase in uh, finally certifying the am part, which is also called as a design for additive manufacturing, right? So this is a very important aspect. Once that is cleared, in fact we'll fabricate and try to validate, and then subsequently we will try to certify and see if it is meeting to our end application when we go through for this weight optimization sort of a scenario. If it is not satisfying, in fact we will try to optimize, and again it goes through a kind of a looping process. And finally, once it is satisfying our final application, we try to freeze this process flow and then go for actual production. Okay, so now with this background, probably I'll try to now onwards go through some of the am technique, which I guess most of you might have aware of. The techniques such as fuse deposition modeling. I have a video here which would be very better to understand through this video. Yeah. I hope the audio
Fused
is
deposition modeling, or FDM,
coming to.
is a layer additive manufacturing
Yes, sir,
process
it is
that
clear.
uses
Yeah,
production-grade thermoplastic materials to produce both prototype and end-use parts. This technology is known to accurately produce feature details and has an excellent strength-to-weight ratio. FDM is ideal for concept models, functional prototypes, manufacturing aids, and low-volume end-use parts. The FDM process begins by slicing 3D CAD data into layers. The data is then transferred to a machine, which constructs the part layer by layer upon a build platform. Thin thread-like spools of thermoplastic and support material are used to create each cross-section of the part. Similar to a hot melt glue gun, uncoiled material is slowly extruded through dual heated nozzles. The extrusion nozzles precisely lay down both support and thermoplastic material upon the preceding layers. The extrusion nozzle continues to move in a horizontal XY plane while the build platform moves down, building the part layer by layer. The finished part is removed from the build platform and cleaned of its support material. Raw FDM parts have visible layer lines. However, service providers offer multiple finishing options to create smooth, even surface parts, including hand sanding, assembly, and cosmetic paint. Since FDM parts are constructed with production-grade thermoplastics, including ABS, polycarbonate, and Ultem, they are both functional and durable. FDM is utilized in a number of industries, including aerospace, automotive, industrial, commercial, and medical.
Okay, so I hope the video was self-explanatory. So just the point which I would like to emphasize is that this fused deposition modeling, as of now, exploited for thermoplastic kind of material, and also people are using it for producing the composites. In fact, there is a company called Markforged. They are using it to produce the carbon fiber reinforced composites, which can be deployed into aerospace applications. And uh, this particular technique, selective laser melting, as I mentioned in the first slide, by comparing conventional manufacturing process. So this is more for the metal, producing metallic components, and primarily the laser sources would be used. And this is the powder bed, and then eventually this is the laser scanning happens, and then the part prints layer by layer. You can maybe understand more from this video.
Direct metal laser sintering, also known as DMLS, is an additive manufacturing technology that creates metal parts directly from 3D CAD data without the need for tooling. DMLS utilizes a variety of metal and alloy materials, such as stainless steel, cobalt chrome, and Inconel, to create strong, durable parts and prototypes. DMLS is an excellent choice for functional metal prototypes, high-temperature applications, and end-use parts. The DMLS process begins in the same fashion as other layer additive manufacturing technologies. A program takes 3D CAD data and mathematically slices it into 2D cross-sections. Each of these sections will act as a blueprint, telling the DMLS machine exactly where to sinter the metal material. The data is then transferred to the DMLS equipment. A recoater assembly pushes powdered metal material from the powder supply to create a uniform layer over the base plate. A laser then draws a 2D cross-section on the surface of the build material, heating and fusing the material. Once a single layer is complete, the base plate is lowered just enough to make room for the next layer. More material is raised from the cartridge and recoated evenly upon the previously sintered layer. The DMLS machine continues to sinter layer upon layer, building from the bottom up. As the part is built, support structures are added to give supplemental strength to fine features and overhanging surfaces. The completed part is then removed from the base plate and treated with an age-hardening heat process to further harden the part. Any support structures are also removed at this time. With numerous surface treatment and hand polishing options available through service providers, DMLS parts can be used in highly cosmetic applications. Typical uses for DMLS include tools and manufacturing aids, small integrated structures, dental components, surgical implants, and aerospace parts.
All right. So from the video, they also mentioned this technique as DMLS process, which is nothing but direct metal laser sintering technique. So it is also called by that technique, and typically this is one of the industrially proven and commercialized kind of technique, which is having a lot of potential, especially for the aerospace and biomedical, and also recently for automotive applications. People started using this technique because of the fact that most of the material which we use it for these applications can be manufactured easily, right? And the other technique is the electron beam melting AM technology. The concept is by and large same, except the laser in this particular process. We would be making use of electron beam to melt the layer of the powder, and then the sequence of operation happens in a more or less in the similar way. Okay, and of course, in terms of the cost aspects, the electron beam melting technique is slightly higher compared to the laser, and it has kind of in terms of quality of the part would be slightly better than the SLM process, due to which it finds a lot of applications in the biomedical sector. Okay, and the other technique is the laser engineered net shaping technique. Okay, so this is very similar to the SLM or DMLS process. Only difference is that it doesn't have any sort of powder bed, but in the nozzle that we see, there are powder supply happens, and then from this particular nozzle there will be a laser head attached to it, and then the powder enters through this nozzle, and then the melting happens, and then eventually the part gets printed. Probably this video will give better understanding. All right. So you might have appreciated the difference between the SLM or EBM or this particular lens process. So basically, the complexity is being achieved in this case due to the fact that because of the robotic manipulation one can get, through which we can obtain more degrees of freedom, and then more complicated profiles and the shapes can be obtained, right? And the advantage of this technique is that people make it use for a slightly larger component size, which would be difficult to obtain through the SLM or EBM technique. Okay, so moving forward, we also have another technique called laminated object manufacturing. In fact, starting from the FDM, SLM, EBM, and lens process, you could have seen that except FDM, you have the powder being the starting material. And in the case of FDM, although you start from the solid wire, while printing, it will be deposited as a liquid, right? So that comes under the liquid, powder, and this laminated object manufacturing process. For this, the starting material, in fact, is the sheet, and then you can see a sheet which is more like a solid, is the form of the starting material, and the process would be, easily understandable from this video. All right, so I think the process would have been understood through that video. So basically here, the thin sheet material being, kind of glued or kind of stacked one over the other by slicing them, or cutting them by using appropriate laser beam, and thereby the layer consolidation happens, and then subsequently for each and every layer you try to supply them the sheet metal that is required through the roller arrangement, and then the process happens depending on the complicated, I mean the CAD model of the profile which has been sliced and sent in the form of 2D drawing, right? So now the other technique, in fact, under this process is that binder jet 3D printing process, where here it is in a way happens very similar to our the powder bed technique, similar to the SLM or EBM technique. And there would be a kind of binder which would be sent through this printing head, and then eventually they'll be getting fused with the composition of the powder which we have intended to print or manufacture the part in a similar fashion that we saw from the previous techniques.
Binder jetting additive manufacturing is a process inspired by the technology of inkjet printers. In this process, a liquid binder is selectively deposited on a powder bed with a print head. It is a growing process that allows the production of parts for the manufacturing, medical, and dental industries. This technique enables the production of metallic and ceramic parts as well as sand molds for castings. To start the process, a 3D drawing is imported into the printer software. The powder to be used is placed in a dispenser, which ensures a constant supply during printing. First, a powder layer of a specific thickness is spread. Thereafter, the printing head, moving on 2 axes, projects the binder where necessary. Before moving on to the next layer, the solvent contained in the binder is evaporated by an incandescent lamp. The powder bed is then lowered and a new powder layer is deposited. Therefore, the production takes place in a series of steps that build the part layer by layer. When the cycle is completed, the binder is cured by placing the container in a furnace. The temperature and time depend on the type of binder employed during printing. After this step, unbound particles are removed to reveal the part or the mold. After this step, the sand molds are ready to be used in foundries. The metal and ceramic parts must undergo sintering, infiltration, heat treatment, or hot isostatic pressing before being used.
So yeah, with this technique, in fact, in the as printed condition, it is not suggestible to use them directly. We have to do appropriate post processing, like the sintering, when we use our powder as a metal powder before we get into the actual deployment in the actual practical scenarios. So in that way, in fact, we can think this process very similar to our powder metallurgy route. So thereby the sintering mechanism phenomena, and also the shrinkage associated during those sintering, all those things has to be a priori calculated, and then accordingly we need to design our CAD model so that it can take care of the shrinkage compensation aspects also. Okay, so there is another technique which is a polyjet technology, very similar to the binder jet, but only thing is that it would be more towards the using the UV lamps for curing our starting material, and then eventually getting the layer by layer kind of fashion. So maybe we'll look at this video to understand better.
Polyjet is a layer additive manufacturing technology used to develop plastic prototypes from 3D CAD data. This rapid prototyping process uses inkjet technology combined with UV curable materials to quickly and economically produce highly detailed and accurate physical prototypes. Polyjet is one of the fastest prototyping processes available to develop high-precision physical parts, and is ideal for smaller parts, appearance models, and master patterns. The Polyjet process begins by slicing CAD data into cross-sections or layers as thin as 6/10,000ths of an inch. data is then transferred to the PolyJet machine, which begins constructing the object one layer at a time. Similar to how an inkjet printer lays down pigment, the PolyJet printhead deposits small amounts of ultraviolet curable material on the build platform, eventually forming a single cross-section of the part. An ultraviolet light attached to the printhead simultaneously cures the material as it is printed. Once a cross-section is complete, the build platform is lowered slightly to make room for the next layer. As the part is built, support material is added to give supplemental strength to fine structures and down-facing surfaces. After all of the layers have been created, the finished part is removed from the platform and cleaned. Although finishing is not necessary, a number of hand sanding and paint options are available through service providers such as Solid Concepts. PolyJet parts are well suited for quick, economical prototypes requiring exceptional detail, surface finish, and edge visualization. PolyJet is ideal for a wide range of industries, including medical, entertainment, consumer products, automotive, and industrial design.
All right. So maybe maybe in the interest of time, we'll move further. So although we saw all those techniques from the videos, right? So they're all come under in the classification which I showed you, direct AM technologies. There is also indirect AM technologies, meaning here the AM part or the produced AM component would be not serving as a final product, but that will aid to obtain the final product. Like for example, the these are all the kind of 3D printed wax pattern. Like for example, when we want to do a investment casting, we know that we need to have a wax pattern, and if you have very intricate details and shapes which we need to cast it right as a end product. In fact, people are trying to make use of the 3D printed wax pattern and then eventually use it as in the casting technique to finally get the final product out like this, right? So this is in a way example for indirect AM technology. And then another application is in the case of mold design. Like for example, we know that be it metal forming application or in the die casting kind of a process, the molds which we use undergo a tremendous amount of thermal cycle, right? And then eventually, because of that thermal loading, the life of the mold comes down drastically, right? So what people are doing is that people are trying to develop the molds with internal cooling channels, right? Thereby, in fact, we can control and have a proper thermal management for this molds, and subsequently by doing so we can increase the life of these molds. And we know that the cost of one mold, depending on the kind of complexity which would have, right, the cost is very high, and frequent replacement of such molds would be tedious, and also incurring a lot of investment, right? So in that direction, this AM technology can be used to improve the functionality of such kind of mold, and then appropriately designing these internal channels, one can think of improving the final durability of this component, right? So these things come under the indirect AM kind of applications, and the technological advantage one can think of, right? So now probably there are lots and I mean a lot of parameter, in fact, going to influence the AM part quality or the final part quality which we would be obtaining, starting from the machine For example, when we are focusing on metal AM, not on the FDM, then the kind of metal powder and the quality of it, and the CAD data, how do we slice them, and then plan them for the printing, and also the production in terms of while printing them, orientation, parameters, supports, so on and so forth. And then the post processing kind of things, what kind of stress relieving things, and then the surface finishing. You might have seen in all the process, we need to take out the printed part from the build plate, right? So how do we do that without affecting the damage to the already printed part, is those kind of a thing. And once that is done, we need to do a quality inspection, try to understand what kind of accuracy we are getting, is there any defect, what is the strength, all those things need to be worried. And these are all some of the factors which directly has implications on the part quality of the additively manufactured component, right? And there is also a kind of characterization or certification process which needs to be done primarily for metal based AM technologies like powder bed, electron beam melting, lens, such kind of techniques. We need to before getting into the component level, at sample level, we need to print them at the horizontal position, vertical position, try to see how they vary their property in different orientation. And this is one of the benchmark model in the AM community. They try to first print this and try to see whether the dimension and the shrinkage associated aspects are being controllable, and all those things will be tested before getting into the actual component printing. Okay. And as I said, the characterization of the powder particles, right, is very very important, and that becomes very important especially when we talk about aerospace application. There's a very stringent norms, and then as I said, uh, the powder size is of utmost concern. And typically the for AM technology, the shape and the size of this powder has to be spherical as much as possible, and it should be in the range of something like 40 to 60 micron size. Okay. And these are all some of the grain structure one can think of when we actually get the printed part, right, in different conditions. And there are various tests one needs to do when we think of this AM technique as the process for given application, right from mechanical to metallurgical kind of a testing, and also the microstructure by using different types of characterization techniques. And now some of the for example, challenges associated with this AM, especially metal AM system, is that the design for additive manufacturing is one of the challenge, depending on the shape and the profile of the component that we need to manufacture, and the optimization of part orientation and support. How do we place them, and then what kind of support structure we give, and how do we remove those support removal and finishing operations, right, to obtain final surface finish. And the kind of process or the method of characterization or the certification process adopted is also another challenge. And multi-material selection, for example, when we think of functionally graded kind of composition, then how do we optimize their mm, kind of proportions for given shape and size of the component. And the inspection, as I said, it is also needs to be part has to be properly designed so that this inspection becomes quite easier and faster. And of course the cost is as of now at the at the moment, it is a bottleneck. I hope as the technology matures and then commercialized at a larger scale, this cost with respect to the equipment and consumables are very costly affair as of now for metal AM kind of systems, right? So probably quickly, I think I have another Mahesh, another 20 minutes. So that includes QA also, or we have QA after that? Mahesh, are you there? Okay, I think let me proceed further. So the second part of my talk is on the role of AM process on the remanufacturing strategies in aero industries, right? So you see, I mean, the kind of research work as of now with respect to AM technology is growing in a yearly basis in a faster way, and it is picking up, especially for aerospace application in a significant proportion compared to other application area. And there are really a lot of benefits one can get from this AM, right? From in terms of lightweighting, the part consolidation, and also the repair functionality. All those things will finally give us in terms of better performance and efficiency, especially from the viewpoint of aerospace applications. And then the sustainability, all those things can be thought of. And now if you look at the kind of AM technology adopted in aerospace industry, right from Boeing, they started using it for mass productions sort of application. In terms of Airbus, they are using it for lightweighting, almost like they saved a kind of weight in A350, close to ton of materials through this technology. And G, they have already started printing certain parts, roughly about in the engine, their engine being very cost effective in the range of 40 to 60%. So this is the kind of scenario for aerospace application. And then the part consolidation, which I told, it is also attracting significantly in aerospace industry. Like if you have, let's say, one part here, one part here, and then another part. So three parts are assembled together to get the final application. Can we, make them single part? So this has been tried out, and then this is how you get a single part. We call it as part consolidation. Okay, so the benefit is that needless to say, weight reduction, and then time can be saved, cycle time decreases, productivity increases, so on and so forth. And this is again for consolidation of parts, especially for in the GE, the where you see almost like 20% of fuel has been saved by using this particular lightweighting or part consolidation. And again, for the GE in the LEAP engine, people have used 20 parts, replacing 20 parts which used to be welded, has been done as a single part through aim technique. And there is a again the weight reduction of about 25% has been seen. This is one of the nozzle, fuel nozzle tip, which has been commercialized, and then it is upon there running real time as of now. And the lattice structure application, as I mentioned, people started already using the lattice structure to save the weight, making as a lightweighting. The benefits are needless to say, we can save good amount of weight, thereby fuel consumption can be minimized to a greater extent. And the topology optimization is one of the key for such kind of lattice structure, where the original design, which is more like a solid part, can be iterated through several design activities, and then finally you can get optimized structure, which can be more like lattice structure based, thereby the lightweighting can be accomplished, right? And the case studies are numerous. I've just given for example, people have already used this lattice structure kind of concept for turbine blade development. Even in the UVV application has been looked at as a promising kind of scenarios. Now quickly, let me get into the application of this AM in the remanufacturing. of aero engine component in a global scenario. So if you look at the role of metal AM techniques, especially for repair strategy, has been catching up in the recent times. Although you can see this is the kind of breakup in terms of what is the usage of AM in different scenario, like R&D, prototyping, production, jigs and fixture, and then the bridge production, so on and so forth. But of late, this repair and maintenance is also gaining a lot of importance, and that's how this remanufacturing or repair could be kind of another application from this metal AM technologies, right? So quickly, some of the applications where this concept has been deployed, as you can see, this is a kind of oil pump gear shaft used in the aero engine component. It These are all the worn out areas during service condition, and because of which once it worn outs, these components would be discarded, right, due to their dimensional inaccuracies and loss of the dimension. So the idea is that can we repair just because this worn out area is gone? If we discard, probably we may need to have a newer component which would be expensive, time taking, so on and so forth. Then the idea is, why not to repair only these location, thereby we can again restore the dimension and then put it back to the service, right? So that is the idea. And you can see that this component has been deposited by this DMD technique, nothing but direct metal deposition or lens technique. So we can deposit and restore the dimension, and with minimal post finishing operation, this job is the component is retrieved or reclaimed from its damaged sort of condition to a repaired condition, right? So this is how the component would be repaired. Like this is the lens system or DMD system through which we try to supply the powder and deposit. Before deposition and then after deposition, we need to do characterization in terms of looking at their interface, and also try to understand is there any microstructural changes for the parent material, HAZ, so on and so forth, and quickly assessing the micro hardness at this interface, trying to understand how good is the interface, so on and so forth. So these kind of studies are routine in this repair application, and it has to be done at the sample level, and then would be finally with the optimized parameter, we would be doing it on the actual component level. Okay, so there is another application where the turbo engine components are typically made out of different sectors, like this is the it's high pressure a flange where they would be worn out at this location, and then which can be repaired at ease with this laser metal deposition or direct metal deposition. It is called by different scenarios, and it is a nickel based alloy. And this case study is from a titanium kind of alloy, where again the worn out of this particular grooves can be again repaired by depositing this titanium based alloys, and then eventually these expensive material components can be reused. Okay, and this is the application of the uh, compressor blades and the blisk profiles, okay, which is again got damaged, and then you can see that it has been repaired and then restored its shape, and then aerofoilic kind of a profile. All those things can be again reclaimed, and then it can be put back to the actual service conditions, right? And again, for the turbine blades, especially the tips are more prone for damage, and those tips can be again repaired by depositing materials like this, and then eventually the dimensional accuracy and also the dimensional restoration can be obtained. And this is another example of the gas turbine ring, where the material again can be restored and the dimension can be restored. Subsequently, it can be put back to the service condition. And this is a case study of when we have thin walls, especially for the turbine blades, right? So it becomes very challenging to avoid distortion kind of scenario. So then the repair work has to be done very meticulously by optimizing the processing parameters. And also this is more like a multi-layer cladding, or the deposition, which would be again done on such thin walls. Okay, so this is again some of the application which has been done by what is known as DED process or DMD process, direct energy deposition process. DMLS is nothing but SLM process. So these are all some of the components which is being repaired and then refurbished. And this is my final slide, where I would like to conclude saying that there are tremendous amount of potential is there from this AM route, typically from this DED or DMD process and the DMLS process. They have significant role to play to reclaim and then remanufacture the damaged components, especially used in aero engine application. As we know, the materials which is used for aero engine applications being very expensive, the manufacturing route and the cost and the material are very very expensive. And if we can, because of very insignificant material loss, to discard such a big part would be not economical. If we can see that the component can be revived and repaired, and then if it is satisfying the structural integrity, and it can perform to the end application or the requirement, we can make use of these two techniques, and then finally have a lot more saving in terms of both material component and the cost, and also the time involved in the whole process of replacing a new material. So yeah, thank you very much for your kind attention. If there are some questions, I'll be happy to answer them.
Yes, participants, if you have any queries, you can unmute yourself and ask the doubt directly to the speaker. Else, you can even write in the chat box if you have any queries. So meanwhile, I have a query.
Yeah, please go ahead, Mahesh.
Sir, when we deposit layer by layer,
Yeah.
is there any chance that the bonding is weak, or any kind of a porosity or defect that occurs between the layers?
Certainly, yes. This is very common when we deal with the metal AM processes like SLM, E-beam process, or lens process, right? So that happens when we don't, for example, optimize the processing parameters. Like for example, in the case of SLM process, we have the laser power, okay, and the laser scanning speed, okay, and the layer thickness, and the hash spacing, and there are other processing parameter. Like for example, if we take the laser scanning speed, it is very similar to, for example, the welding process when we do, and what is the welding speed that we use to draw a bead, right, or weld a bead. So in that scenario, if we are using very high, let's say, scanning speed, then the scenario that we are going to encounter is that we are going to have improper melting of the metal powder, right? And then once this improper melting happens, then there could be associated defects, like as you mentioned, unmelted zones will be there, some porosities will be there. For example, when we are using very high laser power, not only melting happens, in addition to melting, the metal starts to evaporate, and then if it is a evaporation process, then there is loss of material there that can associated with something like porosity sort of scenarios. So optimizing the parameters is one of the very key important step in the metal additive process.
Mm. So, one question from the participant.
Yeah.
Sir, at what thickness layer is printed?
Okay, so basically as of now, for materials like the titanium and superalloys, which are used for, let's say, aerospace applications, right? So there they have the layer thickness to be in the range of 20 microns, 30 microns, and that would be the optimized kind of layer thickness, because the laser beam that we are trying to make use of to melt the layer, right, that has to penetrate through your entire layer so as to obtain complete melting and then quick solidification, right? If we use, let's say, 100 microns or 1 layer to melt them, obviously your laser beam or the electron beam will not able to penetrate for entire thickness, right? Then apparently you'll be ending up in improper melting. Melting will only happen at the top surface but not at the bottom surface in the 1 thickness. So usually the ballpoint figure for this layer thickness is around 20 to maximum 40 microns for most of the materials. We can't go beyond that. So that's why this process is also takes bit longer time, because you are melting micron level layer thickness, right? And that is a, as of now, bottleneck, but people are working towards improving the this particular increasing the build rate.
Okay, thank you, sir. There is another couple of questions. Question from Mr. Sandeep is that, is there any chance of stress development in the part, like residual stresses?
Definitely yes, because it is as good as the process very similar to the welding process, if you can, if I can give the analogy. So obviously you will see that we do a lot of fixturing when we do a welding process. If we don't do a fixturing, you will see distortion or warpage of the weld plate, be it a lap joint or a butt joint, right? So that is happening because of the cooling rate which happens, is it not? So especially in the case of this laser based additive manufacturing process, or electron beam based additive manufacturing process, the cooling rate is so high. It will be in the order of 10 power 5 to 10 power 7 Kelvin per second, right? So because of which rapid solidification happens, which is one of the characteristic of this process, due to which there will be accumulation of residual stress. And if you look at the component once the printing is over, and if we try to measure the residual stress by using appropriate technique like X-ray residual stress analyzer, you will see that tensile residual stress signature will be there. And to get rid of that tensile residual stress, that's why we go for post processing like stress relieving activity.
Okay, thank you, sir. Uh, Another question from a participant, Akash. Is this process cost efficient and environmental friendly? And is this capable of producing mass materials, like
Well,
mass production probably?
yeah, I mean, okay, the mass production, as I said in the earlier slide, it is only economical when we have more like a batch type production or low quantity production. Okay, but however, it would be great. As of now, the bottleneck or the challenge is that the cost in terms of the material and the equipment. So because of which it can't definitely compete with the conventional manufacturing route for the mass production. So which means it will be for low quantity type batch production sector. And what was the first two questions, Mahesh? Can you please repeat?
Yeah, like, is there any, sorry, 1 minute, I just, Is this process cost efficient and environmental friendly?
Okay, the cost effective, as we have seen, as far as the complexity of the part that we want to print compared with conventional manufacturing technique, yes, it is cost effective. And when your quantity of the part to be produced is less, obviously the conventional manufacturing process will have very high cost compared to AM route. So given these two conditions, the AM technology is cost effective. And coming to environmental factors, definitely there is a sort of edge compared to conventional manufacturing process in terms of recycling the scrap material. For example, through conventional route we will be recycling it, and during recycling again you have to melt, and because of the carbon footprint and things like that, you have the environmental, pollution associated effects. So in that way, we can to some extent say that AM technology is green manufacturing technology. Although for producing metallic powders, right, you have to again melt them and make use of certain energy, right? So but yeah, there are here and there pros and cons are there, but looking at manufacturing as a route, this route is having economically sorry, environmental friendly sort of a route, since we have minimal wastage of the starting material,
Okay,
unlike conventional machining process.
okay, sir. Sir, another question. Uh, just how can the weight is reduced for the same component manufactured by AM process?
Yeah, I showed, right? I think when we are trying to scoop out the material, like for example here, this is the turbine blade, and we know that the conventional turbine blades used to be solid, right? And now we are trying to remove the material by placing a kind of lattice structure, due to which you obviously don't have material, and there is a kind of material saving, and thereby the weight of the total turbine will come down, right? So because of which we say that it is a lightweighting. And of course nothing comes free, right? Like when we don't have material, obviously the structure load bearing ability has to come down. That is what we assume or we think, right? But the lattice structure would be created in such a way that it can, despite of removing the material, it can endure or perform or bear the mechanical loads. That's how we say lightweighting.
Okay. So one more question.
Yeah.
Is that possible to use AM process for manufacturing of super alloys?
Yeah, certainly. Like for example, people are making use of Inconel 7 and 8, okay, AM process, because it is AM friendly material, okay. And people are also making use of, for example, uh, exotic nickel based alloys such as CM247LC, which is another class of nickel based alloy. And also people are trying to produce single crystal turbine blades, which is again nickel based kind of alloys. So it is possible, and typically AM nickel based alloys are AM friendly, which means they are weldable or meltable, and eventually which can be printable also. Yes.
Sir, if your time permits, can we have last two more
Yeah,
questions?
yeah, please go ahead, go ahead.
Uh, there is another question from a participant. Aero industries are now adopting single crystal turbine blades for high temperature applications. So are these manufacturing processes are as efficient as them in high temperature applications?
Well, what I'm understanding is it the question in terms of this AM route or the manufacturing technique can be efficient compared with the conventional manufacturing technique?
I
Is that
think
the
it is
question?
the comparison between a single crystal
Okay.
and same product produced by AM process.
Okay, so yes, as of now, the challenge in terms of single crystal is that how do we maintain the crystal orientation to a certain, crystal plane, right? So that is achievable as of now through conventional route, like the single crystal formation or directionally solidified kind of approaches. That is possible, but in the case of am route, it is still in the research phase. Okay, and obtaining, let's say people are in fact trying to obtain this turbine blades through I mean by you making use of single crystal through am route. As of now, to obtain, let's say, the height of this blade, if you assume to be 100 right, as of now, to obtain the single crystal nature throughout that 100 height is becoming a challenge through am. But nonetheless, still the research is ongoing, and I think it should be possible. It's the question of how do we manipulate and optimize the process parameter.
Okay. So the last question, there will be some set of time for every material. If we build a large component, how we say that quality of product is good and durability? Because the last layer gets cooled, right?
Yeah,
Example, rocket nozzle.
yeah.
That is a question.
So it is more towards, like, especially for the bigger parts, it can be you can see that the layer by layer kind of approach. So the heat for, let's say, the latest layer which has been printed, maybe the last layer, right? So that particular heat would be quickly dissipated through one to the same subsequent beneath layers, and finally to the build platform. Okay, and also to the ambience. Okay, so now the heat extraction from this large part is not going to be a great challenge. What is great challenge is that if we have uh, varying sectional thickness. Let us assume now example of this turbine blade. We have a very thick section at the bottom, and then quickly it has to move towards a thin aeropholic kind of a blade profile, right? Then how do we synchronize the solidification behavior or phenomena at this interface where you see the drastic change in the sectional thickness, right? So this is the kind of very challenging I would say region which need to be optimized by manipulating the process, right? So maybe I would like to put the question in this way: there is no challenge in terms of obtaining a larger part, but the challenge is there in the larger part if you have these kind of change in the thickness. That is where is the challenge, and which can be addressable. That's not an issue. It is a question of how do you optimize your parameter there, and then try to have the structural integrity, and then obtaining required microstructure which can perform or deliver the intended mechanical property.
Okay, sir. Last question, sir.
Yeah.
Is there any threat with handling laser power at big scale? And is there any chance of for radioactive problems for
No,
workers?
the thing is, as of now, there are a lot of safety precautions when we do the powder bed kind of a process, right? So it is we need to, of course, exercise a lot of safety accessories. Like we need to wear a goggles. There are some sort of electrostatic aprons, kind of a clothings, right? And the gloves, all those things, safety measures has to be exercised, and the entire process happens within the controlled and closed chamber. Okay, so then there is no issue of any
health or safety related things. Yeah.
Okay, sir. Which Indian industries are adopting these technologies? This is the last question.
Okay, so there are already a lot of industries. Since it is Indian industries, you can think of, the Tata Group is thinking seriously, and Bharat Forge, okay, and in the automotive sector, and in the aerospace and defense, already a lot of DRDO labs are started appreciating this technology, and they are making use of this technology in their engine programs and missile programs. Okay, so in the aerospace sector it is there, and a lot of biomedical industries, although I could not name which type of industries, but in Bangalore, to my understanding, we can see Wipro. They are big players. They are doing a lot of job for defense, biomedical, automotive, and there are startup companies like Rapid DMLS, Intech DMLS. These are all few companies which they started as a service-based kind of industries.
Okay, sir. Thank you
Yeah,
very much, sir.
yeah,
Uh,
Yeah,
so,
hello, hello. Yes. Uh, so I have one question, sir.
yeah. Please go ahead.
Regarding turbine blades, sir. Turbine blades outer layer has to be high thermoresistive and high temperature sustainable material.
Mhm.
So we should have the material which can sustain for longer time and has to maintain higher temperature or the heat dissipation.
Right.
So what are the cooling system challenges in AM technology, sir? Because in earlier existed turbine blades,
Hmm.
we have different impingement techniques that those are cooling systems. So what are the challenges we need to face in case of AM technology?
See, for example, in terms of the cooling holes which we can provide, right? Like for this turbine blades itself. So one thing is that if you can have these kind of lattice structures, right? No more your entire blade is solid. You have a lot of this lattice structure. They themselves behave like cooling channels. And number two, if the design is not permitting these kind of a thing, people are trying to have the through cooling holes, in this blade profile itself, which can take care of different types of cooling techniques like impingement, transpiration, such kind of a cooling methodology. So that is possible. And there are, of course, techniques like you might have come across the thermal barrier coatings on the AM printed part itself, right? So they can in fact take care of that thermal loading which comes onto the turbine blade surface. So in fact it can be coupled approach. If you can have the AM printed turbine blade, and then you do the conventional surface engineering technique like thermal barrier coatings, it can be a double advantage, right? So that sort of approach also people are trying to try out. But yeah, it is there are challenges. It is not that straightforward and cakewalk. A lot of sample level experimentation one has to do before arriving at the component level stage. So there is a definitely a challenge.
Yeah, okay, sir. Yeah.
yes. Thank you, sir. Thank you for your great informative lecture detailing about the additive manufacturing processes. And we are very glad to have your session, sir. It was very nice where students and the participants could able to understand in detail. And thank you for your valuable time and very patience in clarifying the doubts. So I would like to thank you once again. And it was a great session, sir. Thank you very much.
Great. Thanks, Mahesh, for the opportunity. It was my pleasure. I also enjoyed talking to you people, and yeah, so hoping to again get connected with a similar kind of future programs and lectures.
Yeah, sure,
Thank
sir.
you very much. Yeah.
Thank you very much. Thank you. Thank you to all the participants for your enthusiastic participation. So in the afternoon, we have another session at 3 o'clock. So kindly join well within the time. Thank you.